How's it going, everyone? Happy to see you all. I'm glad that people still come to class and all that sort of stuff. Uh, turn off down these lights. How have the last 2 weeks been? Yeah, I mean, the math is getting more difficult, certainly. One more week to go. This is the final class, final new material that will be fair game for the final exam. We'll have, after that, 2 days of review in class, right? Wednesday and Friday. Wednesday's class will be a bit more of a guided review, similar to what we've done in the previous tests and midterm and what have you, where I provide a list of problems and you can vote and whatnot and tell me which of these problems maybe you're most interested in hearing about. And of course, I'll write up solutions to the other problems and post those onto D2L so that you can look at those. And then Friday's class will be a bit of a free-for-all, where you can propose your own questions that you'd like to hear me discuss. I do this a little bit reluctantly each semester, just because what can happen is that folks can go out and find a very difficult question, right? You go and you look at your web work, homework, and things like this, and you can find a question that probably took you, 20, 30 minutes and whatnot. In order for me to do a good, thorough explanation that makes sense, it would take me 20, 30 minutes at least, right? And I'm not sure if that's the most beneficial use of study time and review time in class, just because, right, such a difficult problem maybe is not reasonable for a time setting like the final exam. And so what I would encourage you, right, when you're thinking about questions to ask in Friday's class, right, just think about something in the Goldilocks zone, kind of in the middle of the road sort of deal. Not really, really hard. Of course, not really, really easy. I don't think there's much chance of folks asking really easy questions for review, but resist the urge to ask a very, very difficult question just because, I can spend the 30 minutes discussing it, but I'm not sure if it would have a ton of value, if it's the computations are just difficult or something like this. So that's the remainder of our classes together here for this finals week. I do plan on coming and, teaching each day this week to hopefully put my thumb on the scale as best as I can and see you off, to great success on the final exam. So that's my hope for this week. Otherwise, there's the post-course survey. I'll mention that there are a few things in my folder as well to kind of help you think about and prepare. So again, this is under my folder in D2L. I've released, I went out and I found, sometimes in previous semesters, students have told me that the true-false is sometimes quite difficult. It's more conceptual typically. And so I found a great list of true-false questions online. I've read through all of these and I've told you which ones I don't think are especially appropriate for our class, so you can exclude those. And then they have detailed solutions. So I think that's quite nice as well. There's also a final exam checklist, similar to the other tests and midterm and what have you, that you can take a look and hopefully double check and make sure that you're relatively happy with all of the content that we've gone over in class. And if not, right, it gives you kind of something to help guide your studying, help choose what sections you should spend your time on. So I think that's a good administrative overview. Any questions really about anything before we start into divergence theorem? Yeah.
Like, is it this entire 16?
Yeah, so the question was, what is on the quiz? And no, it's not the entire everything that we've had since our online test 2. So let me go here really quick to the quizzes folder, because I'm 90% sure I know exactly what the sections are, but it's very unlucky to say the wrong thing here. So it's better just to go here and look. So yeah, for quiz 7, 16.7 through 16.9. So today's stuff is fair game. Stokes' theorem was 16.8. Surface integrals were 16.7. You may have noticed in last week's announcement that it also made a practice quiz that's here in the quiz folder as well, that covers these sections that aren't getting covered on quiz 7. So if you'd like to see what and these are questions that got asked in previous semesters for quizzes and for exams. So they're like good, reasonably strength problems, right? They're not really difficult or really easy or anything like this. They're in that Goldilocks zone. And so that's the Green's theorem was 16.4, both the circulation version and the flux version. 15.6 was surface area with explicit functions. 16.6 was surface area with parametric functions. So some good questions there. Good. Any other questions about anything? Okay. So then we need to transition and start talking about the math for today. Of course, we had a pre-class video, and I'll go over that here in just 1 second. But I do want to, point out or think about that we've had kind of the same storyline now twice in our class, once with lines and line integrals, and now again with surface and surface integrals. So for instance, back in 13.3, we defined arc length and we calculated out arc length. You were given quite often a parametrized curve or something like this, and you were asked to determine how long the curve was, right? And then later on in chapter 16, we did adding up other things along the curve, right? Rather than just the length, we imagined that we were a whale swimming in the ocean and eating up plankton, right? And adding up how much plankton we ate as we went along some curve, right? So you can add up other things along a curve besides just length, right? And this gave us line integrals with scalar functions. And then, of course, in that same section, 16.2, we upgraded and we have line integrals with vector fields, right? This gave us work, adding up how much work was done by some vector field as, maybe particles moved across some curve. And then we also had a couple of sections of tricks that sometimes line integrals with vector fields could be calculated in other ways besides just in the 16.2 method. One of those tricks was the fundamental theorem of line integrals, which is when you have a conservative vector field, right? You can do the f of b minus f of a stuff. And the other one is if you have a closed curve, right? You could use Green's theorem. So these were different ways that we could calculate out line integrals if certain conditions were met, right? They didn't always work, but right, if certain conditions were met, we could use these tricks. We've done the exact same thing more or less now with surfaces, right? We've had surface area, right? So instead of asking how long a curve is, a two-dimensional object, right? The natural question is, well, how much area would it take up, right? How much paper would you need in order to build this, right? So we did surface area. Then we did surface integrals with scalar functions, right? So we added up with scalar functions and we did some surface integrals. We also did surface integrals with vector fields, right? And we did flux. That was the second half of 16.7. And then we are talking about tricks for these last two sections, right? Which again, they don't always work, but if certain conditions are met, right, then we have some tricks. So Stokes' theorem from 16.8 and now divergence theorem from 16.9 are some tricks in order to calculate out surface integrals with vector fields. So the same storyline has basically happened twice, once with lines and now once with surfaces. So I just wanted to kind of help you organize this in your mind, kind of how these all are fitting together here. So I hope that that's helped some. Now let's kind of transition and talk about the pre-class video. So the pre-class video, like I said, this is one of the tricks. It's an upgrade from Green's theorem. So Green's theorem, the flux version of Green's theorem, right? We noticed that we were calculating out this divergence and just doing this a double integral since we were in just the XY plane. But if you were to upgrade this, right, and now we are in XYZ space, then we have, now a Z component, right? And so now you're going to need to do a triple integral as well. So this is the upgrade. It's at least reasonable that this would be true. And then the post-class video, right, I give a more detailed proof about, okay, this is at least hopefully semi-convincing that this is reasonable for a theorem. But then, of course, if you want the full proof, this is available in the post-course video. So I invite you to watch that. Of course, the last thing that we did is we did a example with this, but we'll do many more examples in today's class. Admittedly, I've chosen too many questions for today's class. I think it's like 6 pages long or something like this. I'll be lucky to get through 4 pages, but as always, I'll post the solutions to the other problems on D2L after class. All right, so that's about it for the pre-class video and, this extra stuff, concept mapping, whatnot. Any questions about any of this before we start on the new stuff for today? All right. Well then, why don't we go ahead. And here is another problem, right? So evaluate out this flux integral. So a surface integral with a vector field here. We're given the vector field and we're given a surface, right? Over here is our surface. We have the picture and we have lots of equations going on here. So the first thing that we have to recognize, right, is when can you apply the trick, right? When can you actually apply divergence theorem? Because even though we're in a section about divergence theorem and we're, naturally just going to be interested in applying the divergence theorem, right? Nowhere in this problem does it say use the divergence theorem, right? So if this showed up on the final exam, you have to decide, are you going to do this in the same way that you did in like 16.7 and you just calculated out flux, or can you apply one of your tricks, right? So of course, Stokes' theorem, your surface integral has like the curl of f dot ds. Here we don't see a curl of f dot ds, and so Stokes' theorem is probably out, right? You can't really make that exchange for, you write the surface integral of curl of f dot ds to a line integral if you don't have curl, right? So, okay, Stokes' theorem's out. Now the question is about divergence theorem. Well, divergence theorem, similar to Green's theorem, right? It needs to completely surround, in this case, a 3D region. So when we look at this surface here, and with all these equations, right, we talk about E is bounded by all of these different surfaces. So it does sound like that, yes, it completely surrounds some 3D region. And so in that case, when you do have some surface that completely surrounds a 3D region, it is fair game to go ahead and exchange, instead of your surface integral, to go ahead and do a triple integral over the region that these surfaces surround. Now, you'll see that this will still take us a little while, but if you weren't to think about divergence theorem and just say, well, I'm going to calculate out flux like we did in 16.7, notice that you have this back plane here, this slanted plane here, this bottom plane here, and this curvy bit here, which maybe I'll do like green or something. This curvy, it's not a plane, but some curvy surface here, this parabolic cylinder thing. That's 4 different surfaces. Each one of those 4 different surfaces has its own normal vector, right? This ds is hiding a normal vector. So you'd have to do 4 different normal vector calculations, 4 different dot products, and 4 different surface integral double integrals, right? So in order to do this, just using the 16.7 method, it is feasible, but it would take probably an hour. It would just take way too long, right? And so even though technically it can be done for the purposes of like a timed assessment or something like this, aka the final exam, right? Or even the quiz, right? You really can't afford to spend all the time just doing, all of the surface integrals. So you need to recognize that it completely surrounds a 3D region and then trade that in for 1 triple integral. So rather than doing 4 surface integrals, we only need to use 1 triple integral. All right, so, well, let's go ahead and head down that path a little bit farther. So when I calculate out the divergence, right, we need to go along our vector field here. And we're going to be taking a partial derivative, right? For the first component, we take a partial derivative with respect to x. So I'm going to get 1 times y. For the second component, we're going to get a partial derivative with respect to y. So I'm going to have 2y here. And for my third component, I take a partial derivative with respect to z. Well, there aren't any z's. So this is the divergence of our vector field here. Right? Again, technically, this is a del operator, dot product with our vector field. So ultimately, we want to find the triple integral of 3y dv over our region. Now officially, we are back in chapter 15. This is a triple integral just like we did our triple integrals back in chapter 15, which means that we have some decisions to be made, right? We have to decide, should I use spherical integration? Should I use cylindrical integration? Should I use Cartesian integration? And if I use Cartesian, right, should I do dz first or dy first or dx first, right? I have to make these decisions. And so looking at this here, it doesn't look particularly circular or inside of a sphere or anything like this. I see a little bit of a cylinder, but there's more planes than anything, right? It doesn't really look circular to me, even these, right? There's a lot more parabolas. And so I'm not particularly leaning towards spherical or cylindrical in this case. I'm thinking this is going to be just a regular old, Cartesian triple integral. So when I do a normal Cartesian triple integral, my default is dz, dy, dx. So I'm going to start off with that. And then very quickly, I need to abandon this. Can anyone tell me, by looking at this picture here, why dz is not a good integral to start with? Good, yes. You have two different exit surfaces. If I am traveling in my z direction, I hope we can all agree that I enter in all of the time through z equals 0. That's the way that you get into the structure. But as you continue upward, sometimes you're going to be exiting through this, interesting curvy plane. This is the z equals 1 minus x squared, by the way. But then sometimes you're going to be exiting through this slanty plane, which the plane equation in this picture here is given y equals 2 minus z, but you could just as easily solve that for z equals 2 minus y. So you have two exit surfaces, which means you would need to have two different upper bounds depending on what your x and y coordinates were. So this would be a pain, right? Because now we'd have to split this up into two triple integrals, and that's why integrating with respect to z here is not a great choice. However, right, so okay, we're saying we don't really want to start with z, so I could start with either x or y. And the fact that this maybe equation here in my picture, right, has solved y equals, maybe this is the nudge we need to say, well, why don't we try y then, right? Z is not going to work. We could probably do x as well, but let's try y here. So I'm going to try to integrate with respect to y first here. Then I really don't know what to put for the other one, so I'll do dz dx, and I may change my mind, right? I may flip these around just like I did for this first one here if there's compelling reason to do so. Okay, so if I integrate with respect to y first, well, now I need to travel in my y direction. So here we are traveling in my y direction. Here's my y-axis is going off to the right. I seem to enter in through this flat surface. It's part of the xz plane, aka y equals 0. It's on our list here. And then we seem to exit through this slanty plane, right? And this is given by y equals 2 minus z, or this is, by the way, if you were to just rearrange this one. Another good indicator that integrating with respect to y first is a good option, right, is, right, when you list your surfaces, as we have here in the problem, there are only two surfaces that have a y in them. One's going to be a y entrance, right? How do you enter into the surface? And then the other one's going to be an exit, right? If you count up the number of z's that appear in your surfaces, right, you have 3 of them, right? So you have one in z equals 1 minus x squared, you have one in z equals 0, and then you have one in y plus z equals 2. So hence the one entrance but 2 exits if you travel in the z direction. All right, so let's go ahead and set up our bounds here. So for y, it seems like we're entering in through y equals 0, and we exit through y equals 2 minus z. Now, if we were to go ahead and smush this down so that there were no more y's, and all that existed were x's and z's, I think we get something that looks maybe like this. So again, we're smushing this down into our xz plane. So if there are no more y's, then all that are left are x's and z's. And I think everything lives inside of this little hump here. This hump is really given by the outline of this z equals 1 minus x squared. And then we see that there's some points, for instance, where this crosses z equals 0. So this is going to be z equals 1 minus x squared. Again, this is our xz plane here that we've smushed this into. And then our bottom line down here is our z equals 0. So it's where these things cross. All right. Well, now I notice that I have just 2 z equations here. They're both solved z equals. And so I'm relatively happy with my decision to integrate with respect to z next, right? Before it was just a coin flip, but now that I actually see the picture and I recognize what we're doing, right, this seems like a reasonable thing to do next. So if I was to travel in my z direction, and z's go up and down in this picture, right, I enter in through z equals 0, and I exit through z equals 1 minus x squared. My smallest x value is down here at -1, and my largest x value is up here at 1. So when I set up and I do my x integral last, remember these are just numbers here, we go from -1 to 1. Again, this is a triple integral just like we did in chapter 15. So all of the same techniques and whatnot that you use there should come rushing back for triple integrals here. All right, this is the setup. I think setup is quite often the most difficult part. Now we just have to be careful and do the evaluation. But any questions on the setup before we continue on? All right, well, let's carefully do the evaluation then. So first thing I need to integrate is with respect to y. Let me get these down first. So integrating with respect to y, I'm going to have 3/2 y squared. I need to evaluate this from 0 to 2 minus z. When I plug in the 2 minus z and subtract away 0 squared, that'll just be 0. Okay. Then dz dx. Let's go ahead and maybe take one line to simplify. I'm going to bring out the 3/2, that constant there. And then I need to FOIL out carefully 2 minus z quantity squared. So, right, this is going to be what? 4 minus 4z plus z squared. Double check with the firsts, the inners, the outers, the lasts. Hopefully you get this. Now we're ready to integrate with respect to z. So integrating with respect to z, a lot of this stuff's along for the ride here. And we're going to have what? 4z minus 2z squared plus 1/3 z cubed. And we need to input in here 0 to 1 minus x squared. And now I need to integrate with respect to x last. Let's do another line of simplification here. So we're going to have what? 4, 1 minus x squared, minus 2, 1 minus x squared, and that was z squared there, so all of that needs to be squared. And then plus 1/3, 1 minus x squared cubed. Just as before, probably need a line of simplification. Then we can do our final evaluation. So 4 minus 4x squared. 1 minus x squared quantity squared. I'm going to pull off to the side here and try to do this. So 1 minus x squared times 1 minus x squared. So when I do my firsts, I get 1. When I do my inners, I get negative x squared. When I do my outers, I get negative x squared. And when I do my lasts, I get plus x to the 4th. So this becomes 1 minus 2x squared plus x to the 4th. And we can distribute that 2 to each one of these pieces here. I'll do that here in just a second. With the 1 minus x squared being cubed, right? Again, we need to FOIL this, but now like 3 times, right? Or you may remember something with Pascal's triangle. Go a little bit faster, but I'm going to assume that we don't. So I have this 1 minus 2x squared plus x to the 4th. And I'm going to go ahead and multiply that by 1 minus x squared. So there was 2 of them, and then we're going to multiply it by a third one to give us 1 minus x squared all being cubed. So, okay, I'm going to take this 1, and I'm going to multiply it by all these things. We're going to have 1 minus 2x squared plus x to the 4th. And then I'm going to take negative x squared, and I'm going to multiply it by all these things. Right, so I'm going to have negative x squared plus 2x to the 4th minus x to the 6th. So this is going to be 1 minus 3. We have like terms here. Minus 3x squared plus 3x to the 4th minus x to the 6th. Again, this bit with the evaluation, I don't usually find particularly difficult. It's just a bit time consuming and you have to be careful that you don't make a silly mistake, right? There's lots of places where you can make a silly mistake. So just take your time with it and don't make a silly mistake if you can help yourself. So 1 minus, and that goes for me too. This is really a pep talk for me to not make a silly mistake in front of all of you. All right, copy and paste that in there. All right, let's do one more line of simplification and then we'll do the final integral here. It's just because I have a lot of stuff to distribute still. So take this -2 and multiply it by each piece. We're going to get -2 plus 4x to the 4th minus 2x, fourth twice. So -2 plus 4x squared minus 2x to the 4th. Good. Plus a third minus x squared plus x to the 4th minus 1/3 x to the 6th. I'm going to resist the urge to try to combine like terms. And I'm going to integrate like I promised. So 4x minus 4/3 x cubed minus 2x. Okay, this one here, they're the exact same. I gotta combine like terms there. All right. Minus 2/5 x to the 5th plus 1/3 x minus 1/3 x cubed plus 1/5 x to the 5th minus what, 1/21 x to the 7th. And we're evaluating this from -1 to 1. So my final line here, we're going to have 4. When I plug in 1 in for x, we'll get 1. And then we need to subtract away when I plug in -1. So minus a -1 will be, again, +1 here. Minus 2. And basically, this is always going to happen where we have this 1 raised to some odd power will be itself. -1 raised to some odd power will be itself. And so when you subtract away the -1, you're just going to add on another 1 here. So likewise here, we're going to have minus 2/5. 1 plus 1 plus 1/3, 1 plus 1 minus 1/3, 1 plus 1, so on and so forth. Again, why don't we look at this last one and just convince ourselves that that's correct. So -1/21. When I take 1 and I raise it to the 7th power, we get 1. And then we need to subtract away when I take -1 and raise it to the 7th power. So -1 raised to the 7th power is still -1. And so when I subtract away -1, we get 1 minus a -1, aka 1 plus 1. So there's a bit of cancellation that you can find here. For instance, these two here are the exact same. You can combine like terms and what have you. Also this 3/2, the half in the bottom will cancel out with these all of these 2's here. So for instance, this can cancel out with all of these things here. And you can simplify a bit more, but this would be a perfectly fine place to start typing it into WebWork or to put it into your calculator and get a decimal to 3 decimal places for a D2L quiz, I guess, right? The final would be paper. So, any questions on the evaluation or really anything for this problem here? Okay. Well then, why don't we go ahead and try one that's maybe not as long. So this one would be, I think, a bit more reasonable for something timed. We have, again, a vector field over a surface S, where S is the cylinder capped by these planes. So this is an important thing here. We've seen maybe back in 16.7 or whatnot, we now have 2 kind of closely phrased questions. We've seen before where it talks about a cylinder being cut by a couple of planes. And when it says cut, it means that it doesn't include the planes themselves, right? So it's just telling you where the cylinder stops. So the question is, do you have a cylinder, or do you have a cylinder along with its top and bottom? And when it says it's capped by the planes, right, the top and the bottom are included in the surface. When it doesn't say capped, right, and instead says cut, right, this is just telling you where the cylinder ends, and it's more like a toilet paper roll rather than a Pringles can or something like this, right? So the question is, do the top and the bottom, are they part of the surface? So when it says cap, the answer is yes. When it says cut, the answer is no. So in this case, because we have the cylinder and the planes capping, that means we have a region that's completely surrounded, right? And so divergence theorem is a fair game, or a fair option for this one, right? So we're going to be calculating out flux here. The other thing is that it didn't even include in a surface integral, right? It just mentioned that we're going to be calculating out flux. So when it says flux, remember, this is just some key phrase here that means that we're calculating out our good old surface integral. This is flux. We had a variety of ways that we could do this, right? Just like I showed in that concept map at the beginning of class. We could do it in the 16.7 method, right? But this is made out of 3 surfaces here, right? So you'd have to have 3 different normal vectors, and you'd have to calculate out really the 3 different surface integrals and all that sort of stuff. Or there's sometimes some tricks, right? Again, because we're not doing flux of the curl, Stokes' theorem isn't really applicable. However, because it does completely surround some 3D region, that means divergence theorem is applicable, right? And so we can choose to utilize divergence theorem and trade this in for the triple integral of the divergence over our 3D region that we surround. So rather than having to calculate out 3 different surface integrals, one for the top cap, one for the bottom cap, one for the side, right? We only need to calculate out 1 triple integral. So we're going to, of course, choose to do this. I need to calculate out divergence from my vector field. So I'm going to go along component by component, taking a partial derivative with respect to x, then y, then z, adding those results together. So if I take a partial derivative with respect to x for my first bit here, I'm going to have y squared over 2. For my second component, taking a partial derivative with respect to y, I'm going to have y squared over 2. And finally, for my third component, taking a partial derivative with respect to z, I'm going to have x squared. One line to simplify this: half of a y squared plus half of a y squared gives you a full y squared. And again, the region that we're integrating over is the 3D region that's surrounded by the cylinder capped by these planes. So because of this, right? And again, whenever you use divergence theorem and you trade in for a triple integral, you have to then put yourself back in the mindset of chapter 15. We're now in chapter 15 evaluating out a triple integral. We can do spherical, we could use cylindrical, we could use Cartesian, and then we have to ask ourselves, should we integrate with respect to x first or y first or z first? We talked a little bit about, sometimes there's a better way to go than other times. But this time, right, we see that we're over a cylinder. We see x squared plus y squared, which of course looks very great in cylindrical coordinates. Everything's pushing you towards cylindrical, right? And so I hope that everyone, when you see this, you start thinking about, let's integrate with respect to cylindrical. And then you yell at me. Jacobian, right? Anytime you convert into cylindrical, right? This is just like the cylindrical back from chapter 15. You need your Jacobian, right? So we need this extra R here. There's a lot of students who I've seen in previous semesters who do a great job with the Jacobian in chapter 15, and then for whatever reason, come chapter 16, when they're doing these sorts of problems, it just escapes them. So don't fall into this trap. Make sure you remember your Jacobian whenever you switch into polar or cylindrical or what have you, spherical. So, okay, remember our Jacobian, this extra R. Okay, let's figure out our bounds. Well, it talks about, well, I guess at this point, by the way, part A doesn't really talk about what the actual answer is. It just asks, is it positive or negative? And so I'm really starting to do part B here more than anything. Once we have this bit right here, right, we've calculated out our divergence and we see what we're adding up. Remember, any integrals, we're just adding up values of the integrand, this inside function here. And so our inside function is x squared plus y squared. So, and we're adding up these values for each point that's inside of the cylinder, right? So there's lots of points inside of E. And they all have different coordinates, right? An x, a y, and a z coordinate. And this function says, I really don't care about how high up it is. I don't care about the z whatsoever, but I'm taking the x coordinate, I'm taking the y coordinate, I'm going to square those and I'm going to add them together. And so ultimately, when you square things and you add them together like this, right, these are largely going to be positive. I mean, at 0, 0, it'll be 0, right? But otherwise, even at negative values and whatnot, when you square them, they become positive. And so you're going to be adding up lots of positives. And so when you add up lots of positives, right, of course, you're going to end up with a positive answer. And so if this was like a true-false question or something like this, is this result positive, right? The answer would be true, because we're doing a triple integral and we're adding up lots and lots of positive things. Of course, at the end of the problem here, this one we can actually calculate out and we'll get an exact answer. And this will give us a way to just kind of verify. Hopefully we see a nice positive answer at the end of this. All right, so now let's actually go ahead and start with the evaluation, which means that we need to figure out our bounds. Well, this talks about, right, it's capped by these planes, z equals plus and minus 1. So as I travel upward, I'm going to enter in through z equals -1, and I'm going to exit through z equals 1. Of course, these are just parts of the planes. The planes would go on forever, but they're the only piece inside of the cylinder there. So from z equals -1 to z equals 1. And then we're inside of the cylinder of x squared plus y squared equals 1, which of course you can smush this down into the xy plane. And this is just going to look like your good old classic unit circle here, which means that our r's are going to range from 0 to 1, and our thetas are going to range from 0 to 2 pi, right? Because we need to get the full circle. All right, so when I see this, personally, this is what I would do if this was me on, you know, the quiz or the final exam or something like this. I would go ahead and split this up. Again, you don't have to do this. This is an optional thing, but it is a little bit of a time savings. So notice that we have all constant bounds. That's one important thing that enables you to do this. And then you have a function of solely z's times r's times thetas, right? So the r's, of course, are the interesting bits. And then if you want a z function, you can just include ×1. If you want a theta function, again, you can include just ×1. So that's why you grab all of your r's here, get r cubed. And then if you want to, you can put 1 there for the other functions. But we've also seen, I mean, sometimes we don't even include the 1 there. It's just the integral of d theta, right? And that makes perfect sense as well. So when I evaluate this, we're going to have 2 pi. We're going to have 1/4 r to the 4th, and I'm going to plug in 1 and subtract away 0, but that doesn't give us much anything. And then when I integrate 1 dz, I'm going to get z, and then I'm going to plug in 1 minus a -1. So let's see here. A 2 and a 2 cancel with the 4 down there. And my final answer is just going to be pi. So a nice positive number here. So again, this is the answer really to part B. For part A, it was just, is it positive or negative? We said that it's going to be positive even without doing the evaluation. We're adding up lots of positives. What is the actual value? Well, when we evaluated this, we got pi. So again, this is one here that still relies on us using the divergence theorem, but you can see that not every problem is as long as maybe the first one that we did in class, right? You can get some where the evaluation is quicker. The other thing that I want you to notice is that there's been several times that people have asked on Piazza already, you know, what's the content breakdown of the final exam, essentially is what the question is. And it's a tough thing to answer just because, right, you see that this class builds so much on itself. right? So here we are in divergence theorem, and we are doing the divergence theorem, but we also just tested about cylindrical, right? I no longer need to ask a question on the final exam about cylindrical integration if I include this one, because you had to use cylindrical integration in order to solve this one, right? And so it just folds on itself so much. Likewise, when you calculated out the divergence here, right? That really showed up first in 16.5. Divergence relies on a dot product. The fact that we did a dot product here without even kind of realizing, right? So that was 12.3. We've done a lot of math over the course of the semester within this one problem. And so I just want you to recognize that we are kind of utilizing a lot of what we've done previously in the semester, in this problem. And the same is true for when we did surface integrals in 16.7 or when we do Stokes theorem, right? Stokes theorem relies on a cross product, right? So there's 12.4, for instance. All right, well, that's enough of my rant there for this one. Any questions, again, really about anything? Yep.
Surface integral with like the ellipses in the middle of it, kind of like how we do with the line integral. I kind of see flux notation.
Oh, sure. I don't think our textbook really does that, but if another author for a different textbook wrote that, that's what I would assume it would be. So yeah, we do have for line integrals, we have with a circle through it like this to indicate that you're doing a line integral over a closed curve with a positive orientation, right? So counterclockwise is typically what that refers to. And I believe the question that was asked is, could you do something like this for a surface integral? And of course, you would, elongate the circle and maybe make it more of an ellipse, something like this. And would this have the same sort of significance as far as that it tells you that your surface is closed, it completely surrounds some 3D region, and it assumes the positive orientation. And I would say, yes, that would make sense, but our author for our textbook doesn't do that, that I'm aware of, so. Good, any other questions on this problem? Okay, well, I hope to have time for maybe one more here. This one, I'd like to give you maybe a 2-minute head start. So if you would please try this problem out for me. Again, put yourself in the mindset of the final exam. Nothing on this problem says use the divergence theorem. If you choose to use the divergence theorem, which isn't, this is section about the divergence theorem, I want you to think about why are you using the divergence theorem? How do you know when to use the divergence theorem versus when you shouldn't? So yeah, take 2 minutes, get as far as you can. All right, let's talk about this one together. As I walked around, I saw a lot of good work. I hope, even though it wasn't necessarily spelled out with words, right, on the paper, that you saw that you're doing a flux integral, right? This is your F, your vector field, over a surface. So again, this is some flux integral. And your surface is completely surrounding some 3D region. In this case, a sphere. It's quite an easy way to completely surround some 3D region. So instead of doing the flux integral on the surface itself, you can trade this in for a triple integral of the divergence of F, and then you would be integrating across the interior, right, what this surface surrounds. So this E is, right, the inside of the sphere, sometimes called a ball. As I walked around, like I mentioned, I saw lots of good work. And so if you calculate out the divergence, I saw many people who had Z minus 2, which is absolutely correct for the divergence here. And then I'd like to, I started to see people actually doing the evaluation and whatnot, which is good. It's a good way to go. Safe. But I'd like to show you maybe a little bit of a trick with this one. And so I'm going to go ahead and split this up. Like so. So just like any old integral, right, you do this term by term. So you can quite literally integrate the first term and then integrate the second term, but you're also allowed to bring out constants. So that -2 I decided to bring out of the integral here. So then it becomes just the triple integral of 1. Now this is nice because the triple integral of 1 actually has, right, some geometric value to it. Can anyone remind me, the triple integral of 1, what does this mean geometrically? What does this represent? Volume, right? So volume. So I know volume for a sphere. It's 4/3 pi r cubed. In this case, the radius of my sphere is 2. So 2 cubed. So I know the volume of the sphere. So this bit's done. Now, I would like to claim to you that I don't really need much work here to convince myself that the triple integral of Z over the sphere is going to be 0. Anyone want to try to give your best explanation about why the triple integral of Z would be 0? Yeah, you had your hand up first.
Positive and negative Z values, as taking like points in the sphere.
Good. That's absolutely correct. So again, when we do any integral, we're adding things up, right? We're adding up lots of values. In this case, right, we're adding up points that are inside of the sphere. That's what E is, right? It's all of the points inside of the sphere. For each point inside of the sphere, the thing that we're interested in, the thing that we're actually adding up is the Z coordinate, right? So each point has an X coordinate, a Y coordinate, a Z coordinate. We throw away X and Y. We don't care about those. We only harness the Z values. And because there's this symmetry, right? When you have maybe this point here has a positive Z value of 1/2, there's going to be one down here that has a Z value of -1/2. And there's this symmetry about the sphere, right? That there's equal number of points with positive Z values and negative Z values, and they're equidistant apart and all that sort of stuff. There's this nice symmetry about the XY plane that when you go and you add all of these things up, you're going to get 0. Now, of course, you can, where this comes up, if you actually start to evaluate this out in spherical coordinates, it's your phi integral. Your phi integral gives you 0. Your rho and your thetas give you who cares, right? Because when you have 0 times anything, it's going to be 0. So you can, of course, verify this. The final question that sometimes get asked when I pull off such a trick is that, are we allowed to do something like this on the final or on the quiz or what have you? I would say you can, but you should add a sentence to explain what you've done, right? This is not a guess, right? Of course, 0 is a common thing to guess, right? This isn't you looking at your neighbor's answer or anything like this, that this is, that it's 0. And you could just say, right, symmetry about XY plane or something like this. So that's why this has to be equal to 0. Of course, right, if you're at all worried about this, that you haven't given a good enough explanation or what have you, right, you can just do out the triple integral. Again, your phi integral will give you 0 quite quickly. And so you're going to get 0 in this case. So the final answer, of course, let's see, we have 8 times 8, so that's going to be negative 64 pi over 3. So just as a reminder, right, this is a flux integral. This was with an outward orientation. So that means if we drew out the vector field, there would be more heading into the inside of the sphere than there is exiting, right? Because we have a negative outward flux. So that means that, again, the outward flux is negative, and so the inward flux would be positive, aka there's more coming in than going out. All right, one last administrative thing. So my office hours tomorrow, Tuesday, will be online, like they've been for the past couple of weeks. So if you want to attend office hours tomorrow, please come via Zoom. My office hours on Wednesday, I'll be here, of course, teaching and whatnot, and they're just right after class. And so my office hours on Wednesday will be in person. So I'll try to update my whatever profile on D2L to explain that for this week. But I just wanted to make sure you guys knew office hours on Tuesday, online, office hours on Wednesday are in person. All right, thanks everyone. And I'll see you on Wednesday for some review. Of course, I'll post the solutions to the other stuff that we didn't get to on D2L by 4 o'clock today.